Linear regression. So basically, uh, it's a form of supervised machine learning method, and here we deal with real numbers. Means the output of the model will be a real number, and it won't be a probability from 0 to 1. It will be a simple real number. So we have a linear model, and linear model can be defined as, let's say my linear model is h of x. This is my model, which is nothing but summation of I equals 0 to, let's say, m. I have xi and wi. So this is my linear model, and this looks like x naught w naught plus x1 w1 plus, and so on and so forth till x m and wm. Right, so we have total m plus 1 elements, m plus 1 values. Right, so linear regression. So what are the steps to find linear regression? Excuse me. So actually what we are trying to achieve in linear regression, right? So we have something known as a data set. Data set consists of nothing but x comma y, then again x2 comma y2, and so on and so forth. We have such let's say the cardinality of this, let's say this is a set which is d, this is my d set, and the cardinality of this d is the number of elements, number of data points I have is n, total n, right? So this is my given data set, and this is the x value. This is one single attribute, and this is its corresponding label. So we have this cluster of points. Now what we are trying to achieve is this is a cluster of point, and we don't know that there is any relationship between this, like the way this x1 relates to y1, is it the similar way x2 relates to y2? Am I clear? Like, is the relationship between x1 and y1 same as x2 and y2? We don't know that yet, but we believe that there is some relationship. So which means we believe that there is some relationship which is x, or some function that maps all the x's. I'm writing all the x's in a capital form, x's to y. Right? We believe that there is some function that maps x to y's, and this function is unknown, and we are trying to find out this function. Right. So since we are dealing with linear regression, this is some function, right, from out of a family of linear models. This is one such. This is a generalized form of linear regression equation. But let's say that we have only one attribute, which means we have only single x, right? One attribute. We'll take this set as like x is only one attribute. In that case, my linear, my hypothesis, this hypothesis will be nothing but h of x equals xw plus, let's say, w naught, w1 and w naught. Right. This is my hypothesis in two-dimensional space. Right. So I have this function which I don't know, but I want to find that x maps to y function. So I'm assuming that this function is of this sort, right? And that we will assume by looking at the data. So here we will do our hands-on, right? Here we will be dealing with this data, this data from You can download this data from Kaggle. I will give the link in the description below. Yeah, this data set, it has only one attribute and this one level. So this can be plotted this, we can visualize this in two-dimensional space anyway. So this is my x and this is my y value. So this thing is similar like whatever I have written over here, right? So let me just do one thing. Yep, right. So yeah, so whatever I have written here, whatever is written over here, like this data set, this is the same thing. It has x1 and y1, so this is my x1 and this is y1, right? So this is x2 y2 and this is my x2 and this is y2, right? So this is the data, that's the data I have. And since I have that data, so the weight vector that I'll be having will be of w0 and w1. This is my weight vector, correct? This is my weight vector. Or I can simply, since I'm using the b, I can simply write this as w and b, because this is what I'm using over here, right? This is what I'm using over here. So that's it. And my x, my single sample x, right? This x, single x, this is nothing but a scalar. This x is nothing but a scalar. It has 1 cross 1 dimension. This is 2 cross 1. This is also 2 cross 1, right? So this is my scalar, which is 1 cross 1 of dimension. And this equation you're seeing over here, this can be written as, let's say, y equals to wx plus b multiplied by 1. So this is nothing but a linear combination, like y is nothing but a linear combination of x. I can say that this 1 to be as x naught, means I can write this as, let's say, wx plus bx naught, where x naught equals 1. And this thing can be written as, let's say, wb as a row vector and then x and x naught, where x naught is 1, right? So this is nothing but my w transpose x, right? Done. So that was it. And the next step is this is my linear model. Next step is to train my model. And how will we do that? So this dataset comes with, so the dataset over here, so this dataset comes with our own x and y's, means its own label. So what we will do is, since this is our model, and I will let's say this is my model is equals to h of x. This is my model. So what I will do, I will pass a single element from the dataset, from the D dataset. I will pass a single data point, which is x. I'll get its corresponding ith y hat. Like this is the output from the function, but this thing comes with its own y, means this y xi has its own yi, but not y hat. It has its own y. It has its own label. Now I need to know whether, like, how well my model is performing, which is why we need something like, we need some metric to determine that, well, how close is this answer to this y, right? This y prediction, like y hat is to y. If they both are equal, then it's fine, good, my model is working fine. But if they are not equal, then by how far off, like what is the difference between them? So that can be calculated as L2 norm, as y hat minus y then whole square. So this is a metric which is nothing but the squared distance between my predicted value and my y value, my actual level. Right. So let's say you have a data set. Let's say you have a data set like this. You have some points over here. Let's say you have some points. Right, you have some points over here, and this is your regression line. So linear line, linear model. So for this particular xc, this point on the line will be xc comma yc hat, but the point which is actually given in your dataset is xc comma yc, and this is the error. This one, the value you are seeing, this is your error. Right. So that error, that measure, like this measurement is given by this L2 norm. Okay, the difference between this, the predicted value and the actual value. Now so far so good. Now we understood that, okay, fine, that we have a model and it is predicting something, but that prediction is way off than the actual ground truth, which is the label. So how we can, like, what can we do such that our model predicts the actual label? Like the prediction of the model should be like more or less equal to the actual level, right? So in that case, we use an algorithm known as a gradient descent algorithm, and that helps us to reduce this loss. What do I mean by that? Means, let's say for some x, for some xi, you get some yi hat, right? And based on this, you get some loss L, right? You get some loss, let's say Li of that sample. Li is the loss of that particular sample, ith sample. So you get this loss. Now you cannot change x, you cannot change even y, and yi hat is dependent on x, so you cannot even change this yi hat. But what you can change, you cannot even change yi hat by changing x, because x is constant, like x is given, you cannot change x. But what you can do is your this y hat is nothing but x w li xi and some w plus b equals y hat I, right? What you cannot change this x, you cannot change this one, and but you can change this w and b. Exactly why whenever we use gradient descent algorithm, we subtract the gradients from this w and b, because these are the tuning parameters which we have the liberty to tune such that this y will be equal to y actual, like y of the ith sample. This should be equal, this two should be equal, and if this is equal, then that means this loss is nearly equal to 0, which is our goal, right? This loss is nearly equal to 0 means that my model has predicted correctly, right? Now this is fine, cool, but how, like, now the question is, how am I supposed to change these weights? Like, based on what parameters? Like, I cannot randomly change this to, like, add them with let's say random integer or value, or let's say a fraction. By what fraction? We don't know that. So what we need to do is, the logical thing is, what if we can get the relationship between the w's and our L? Means, let's say, by what factor, if I increase this w, will change this L, right? Like let's say if I decrease this by -1, does this go down by +2 or does this go down by -2 or goes up by +2 or +3? We don't know that. So we need that relationship, which is exactly the reason why we calculate this parameter, which is del L by del W. This is nothing but the derivative of L, the loss function, with respect to the weights W. That means this is nothing but the ratio of the rate of change, right? Del is what? Like del L, the difference between the loss function and the difference between the weights. Like if I use W plus some dW, yeah, so what will be how much change will it cause in this loss function, right? So that is what we are trying to trying to get. If we get that, then based on that we can simply use that to reduce this W parameter. So the gradient descent algorithm says that you have your own parameter, like you have one single parameter, and from that you subtract some you subtract del L by del W multiplied by some positive parameter, which is eta. And what is the sense of this? Why are we doing this? So if you look at the loss function carefully, the loss function looks something like this, which is y minus y whole square, y hat. So this loss function, if you see that this is nothing but a parabola, nice and smooth convex function. Del L and del W, if I say this is L and this is my W, del L by del W will give me what? The slope. Slope can be at, and we will calculate the slope at a particular point. Let's say my previous W is W naught, and I'm calculating the slope at W naught. I'm calculating this at W equals W naught, right? And I can see that my slope is one thing for sure, that the slope is negative. If the slope is negative, then this whole value, since this is eta is positive number and it's given in the algorithm, so if eta is positive and this thing is negative, so my whole thing will be what? Will be W plus some positive number delta. So if I from like W naught plus some positive number delta, so if W naught is here and if I add some positive number, then this W will shift towards right, which means this will be the ultimate location, W naught by W delta, and this is nothing but the delta distance. So for any point lying on this half, right, this will give what? Negative slope, right? So which will change this sign and it will make this W shift a bit towards right. That is how we can get to this position, which is known as the global minima. And why this global minima is required? Because in that case del L by del W equal 0. This means that the slope at this curve, the slope of the tangent to this curve at the point where the slope is 0, right? So we are trying to find that this tangent, if this tangent is 0, see that let's say you have a curve like this, right? So now if this is a function of, let's say, f of x, this is f of x, right? So del f of x cross del x equals 0 will give you what? This differential equation will give you some 3 points where the slope is 0. It means the tangent at that particular point will be horizontal to the x-axis. So you will get 3 point in this case, but in here you will get only 1 point because you have only one global minima. Where this function is fully convex function, but this one is not a convex function, right? So that is it. By doing that, we will get the gradient. This is the gradient descent algorithm, and similarly, uh, we can let's say we can reduce the b as well, like from like sorry, and this is not w, but this is b naught minus some that same parameter eta by del by del b. So this is how my weights are being updated. This is how my weights will be updated. Right. Now, enough of theory. Let's just jump into the code. Import the relevant libraries, and I'm using this CSV file, so I need pandas for that. Right. Check the shape. Yeah, it's 700 cross 2. Nice. This one will check all the null values if I have any. So the total number of null values in this entire data set is 1. I have two columns, which is x and y. X doesn't have any null value, but y has. And this is, see, in at location 213, I have a none value, like y is none, y doesn't have any value. If I describe this, like you will see that y has one value missing, and x has all the 700 values. So what we will do, this value is not required, we can chop this off, like we can just discard this. So this function will help us in discarding that entire row, right? So if I just do this and then again check the shape, and if there is any null value in the data set, this will give me 0. This first thing will give me 0, and this shape will be, see, earlier the shape was 700 and now it is 699. Two columns because we have x and y. Describe this. So this is my minimum value that x can take. This is the maximum value in the data set. If I just plot the figure, this is what this looks like, and we can see that we can fit a linear model, means a linear regression line, into this data set, right? This might pass through origin, or no, there's an offset over here, yeah, so it won't pass through origin, I guess. Anyway, extracting the x and y and converting those into numpy arrays. This is a one-dimensional array. We need to convert them into vectors, and also I'm normalizing this, and from where did I get this values? You can see from here, right? Output. Okay, right. We don't need to visualize those out, right? What this will do is, as I have shown you over here, that this one x equals 1, right? So I have only one x. I don't have another, like it's not like what I have. What I have is just x and not x1. I don't have this. I only have this one. So what I will do, I need to append this one and make it enough in this format. That is why we are using the numpy concatenate. This is concatenation function. It will, yeah, like after that, if I do this, yes, so you can see that to each and every single, that whole column of ones has been appended with this previous x, right? I hope it's clear. So, and if I take the single example, like if I take a single example from this one, let's say 0.24, so that means I have 0.24 and 1. So this is my x, and this is a row vector, so I need to transpose this. Let's say this is x is my this t, I need the column vector. Now with that, what will I do? I will append wb times 0.24 and 1. So this will give me nothing but 0.24 w plus b, and this is nothing but my hypothesis. This is my y hat. like for this sample, for the first sample. So since this is first sample, so I'm giving y hat 0, right, for the first sample. So that is the reason why I appended this one, right. Next is calculating the loss. This is I have defined the loss function in this way, and this is the computing the gradients, and you can see that the gradients, if I compute the gradients, and the gradient computation is quite easy, like if you but no. So gradients computation is quite easy if you check this out. That what was my loss function again? My loss function was let's say I have my y minus wx minus b. This is my loss function, right? So this is my L. Now if I calculate del L by del W, this will be nothing but what? This whole thing, which is y minus wx minus b, and then x minus this one. Now if I calculate the del L by del B, in that case it will be similar to minus y minus wx minus b, and since b is here, so it's 1 and minus 1, hence this minus, right? Quite simple. So these are my two things. And a single sample, my single sample was what? 0.24 comma 1, right? Transpose. So which means this is nothing but 0.24 1, right? So and this is nothing but 1. Now can I say that if you look at this one, then this can be written as 2y minus wx minus b. This whole thing is a scalar, so I can multiply that with this metric, and this metric will give me nothing but my del L cross del W and del L cross del B, right? So this is my gradient vector. I can say that this is my gradient vector. So this one will return the gradient vector, right? I have done that one, y minus y hat. This is my y hat. So y minus y hat times y minus y hat times x. So that will give me my gradients, right? And this is the gradient updation rule. So this line implements this whole thing in a matrix form, right? So this is my prediction. I'm predicting it, calculating the loss, computing the gradients, updating the weights, calculating the total loss, and then printing the total loss. If I do it, my epoch was 10. If I do it, and this is the final weights, this was the previous like weight, so this is my final weight after training. If I plot the regression line, see the regression line is much like it fits the graph well, right? And if I want to plot the previous line, like with the previous weights, like if I'm copying this one, previous weights, and if I, let's say, w's w equals np dot array, if I do this, right, np dot array, and do this. So and then what will I do is I'll duplicate this line and then dot w, right? We'll dot it with w. Color will be changed to blue, I guess, if I just compute this one. Okay, all right. So this is my previous line with the weights, with these weights, and this is my after training. This is the line, the red line is the after training line, right? So you can clearly see the difference that my model has trained. And now let's use this model on the test set. Same, describe, yeah, compute the shape, yeah. So this is how my model looks on test set. Clear? We can also use normal equation to compute, like do the linear regression problem. In that case, this is my single line, like this is the implementation of this equation. If I run this one, I will get the weights directly, right? And you can see this is much closer to what I have got by using stochastic gradient descent, right? We'll see that later. So normal equation. Now this is basically computing the loss between the weights I have got from the SGD, like stochastic gradient descent method, and by using the normal equation. So if I, yeah, so you can see the loss is pretty similar, right? So now if I plot the function this to regression line, so this has completely overlapped each other. How am I saying this? If I comment this one out and see, the exact same line is being given by another normal equation, right? And if you want to see the weights, so these are the weights. See, this is the weight by SGD. This is by normal equation. These are pretty similar. See, almost similar, right? Yeah. So that's it. I hope I made you understand what linear regression is, how it works, and why do we need to calculate the gradients. I will also discuss about the loss functions later in later video. But that's it, folks.